Good Friday morning, kids. We're back in the saddle again. Okay. So what we're going to do, you all have this sheet of lecture notes, okay? We're just going to kind of go through and fill it in. Quick review of what we covered yesterday, and then we'll have everything ready to go, and you'll be on your own. Okay. So, for a spontaneous reaction, now remember, that's something that's just going to happen on its own. We don't have to put anything into it. And as we go through this, there are certain things you just need to begin to memorize. This information is going to be one of them. So for a spontaneous reaction, we're talking about the universe as a whole. Delta S is going to be positive. Okay, so that means that we're talking about the universe. We are increasing the entropy of the universe. Okay, that's going to be a spontaneous reaction. Your change in your Gibbs Free Energy, that's going to be a negative value. Okay, and remember, we talked about delta G, like negative NF times E naught. Okay, so remember when we were talking about electrolytic cells, and N is your number of electrons, here's Faraday's constant, and here's your voltaic. So if you have a positive E naught, and again, more and more of this thing should begin to make sense in terms of a big picture. You've got a positive E naught, you can have a negative value here, that's going to create a negative delta G. So no matter how you calculate Gibbs Free Energy, and this is going to be important, we're not talking about Gibbs Free Energy itself. We're talking about the change in this energy, okay? Just like we don't talk about entropy, we talk about a change in entropy. We talk about a change in enthalpy. So that's going to be, it's subtle, but it's important. So we're going to look at, okay, not necessarily what the value is, but how much it changes. So what's going to be important is that, let's say, for example, the change is 10, okay, whatever it is. That means it could go from 100 down to 90, or it could go from 50 down to 40. No matter what, whether you're going from 100 to 90 or 50 down to 40, that change is still going to be the same. That's still going to have that value of 10. So this is what's going to be important. We're talking about the change in these values. Okay. So if you're going to talk about a reaction that is spontaneous at low temperatures, okay? Now again, when I talk about low temperatures, I'm not necessarily talking about like minus, 10 degrees Celsius. I'm just talking about it being below a certain point. So if you're talking about something that's going to happen below a certain temperature, delta H is going to be negative, delta S is going to be negative. So what's happening here is that this term is driving it towards spontaneity, because this means it's an exothermic reaction. Your entropy term is driving it away from spontaneity. So when you look at this equation, if you look at delta G equals delta H minus T delta S. So your delta H term is like a fixed value, okay? So what we're saying here is that I've got a negative delta H minus T delta S, and that delta S is also a negative value. So here, mathematically, if you're into the math side of this, here's what's happening, is that I can't, since I'm going to be subtracting this negative, I'm in effect adding it. So here's what's important. I can't let this get too big. So this is why it has to be below a certain temperature. Because if I'm not going to change this value, I'm not going to change this value. The only variable that I have to work with is this value of temperature. So as long as I keep this part of it below the numeric value of this delta H, the reaction will be spontaneous. So I can't let this value here get too big. Now, here's the other thing that you will see when you have two negatives, or in the next situation when you have two positives. When you have two negatives or you have two positives, you can set delta G equal to 0. Then you can get a temperature where this becomes critical. If you have a positive and a negative delta H or delta S, then you can't set delta G equal to 0 because you're always going to get negative temperatures per Kelvin. So this is going to be one of the most important things you begin to conceptually understand, is that this is driving it towards a reaction. Okay? This is the spontaneous part of it. You have a negative delta H. Mother Nature likes this because he's being given up. Mother Nature doesn't like this part of it because you're increasing the order of the system. So mathematically, I have to keep this part below this. So let's say this is like, I don't know, negative 50, just to make up a number. So this is going to be negative 50. So this reaction is going to be spontaneous as long as this part over here is less than negative 50. If this creeps up to like negative 51, if this part of it, when I multiply it all together, so when this part of it here, if that becomes negative 51, then I'd have a negative 50, not to be confused with Area 51, that's a whole other conspiracy theory. But if this is negative 50 minus a negative 51, then delta G becomes positive, the reaction becomes non-spontaneous. If this is exactly 50, then I'd have a negative 50 plus 50, which is 0, and then the system is in equilibrium. Okay? So that's the big idea that you want to begin to look at. All right. So let me kind of clear this off. Okay. Now, when you're spontaneous at high temperatures, delta H is positive. That was horrible. And delta S is positive. Okay? Now, in this situation, you got a positive delta H minus T times positive delta S. Now, Mother Nature likes half of this. She likes the fact that you're increasing the entropy and you're making a mess. She's cool with this part of it. Doesn't like this because it's an endothermic reaction. So what has to happen here is that since this is a positive value, and I'm just subtracting this because it's a minus T times positive delta S. So in this situation, I've got to keep this temperature big enough so that when I multiply it by this delta S, I subtract a value that's bigger than this delta H. So let's say that this, again, let's just go with, say that's 50, okay? So I've got to have this greater than or equal to 50, so let's say that could be like 51. So as long as this part over here is greater than 50, the reaction is going to be spontaneous. Okay? And again, the only thing that I can do is manipulate this temperature that I multiply that delta S by. So your delta H is a fixed value, your delta S is a fixed value. The only thing you can manipulate is the temperature. And again, because you have two positive values, you can set delta G equal to 0, and you can find a temperature that is critical at. Okay. Now, at any temperature, that's when you're going to have a negative delta H, and delta S is positive. So Mother Nature is going, hey, this is like a winning combination. Because if you look at delta G equals delta H minus T delta S, okay? So I've got a negative delta H, so Mother Nature likes this because it's an exothermic reaction. I've got a positive delta S, which means I'm always going to be subtracting this part of it because I'm increasing the entropy. So I'm going to have a negative minus a positive value mathematically that has to produce a delta G, which is a negative value. Okay? Now, even if the beauty of this is even if you go to absolute 0, even if you drop this temperature down to 0, you're still going to have a negative delta H, which is going to have a delta G. If your enthalpy change is 0, you're still going to be subtracting a positive value from 0, which is still going to get you a negative delta G. So from Mother Nature's perspective, this is the winning combination. Negative delta H, positive delta S, you're always going to get a spontaneous reaction. Now, in contrast to that, if you have a positive delta H and a negative delta S, This is never going to happen. Mathematically, you're having a positive value minus a negative value, which is always going to get you a positive delta G. Conceptually, Mother Nature doesn't like this because of the fact that you've got a positive delta H here. Mother Nature doesn't like that because it's an endothermic reaction. You have a negative delta S, so you're decreasing the disorder, okay? You're decreasing the entropy and you're cleaning up. So you're getting cold and you're cleaning. That's a bad combination for Mother Nature. Okay, now, down here at the bottom, what we're looking at here is that we're taking solid water, and otherwise known as ice, and we're melting it and turning it into liquid water. So let's look at what's happening in terms of signs. My enthalpy of fusion is 6.03 times 10 to the third joules per mole. So notice that this is a positive value. I have a positive delta H. And it's positive because this is an endothermic reaction. I have to dump energy into this system. Okay? I've got an entropy of fusion that's also positive. Now, if you think about why this entropy value is positive, it's because of the fact that I'm going from a solid into a liquid. A liquid is going to have more disorder than a solid does. So Mother Nature is going, this is okay. I got a positive delta H. She doesn't like that because she's got to put energy into the system, but she's happy because of the fact that we're increasing the disorder. So as soon as I see these two positive values, I know that it's temperature critical. When you have either two negatives or two positives, this thing becomes temperature critical. Okay, so we're going to look at two different temperatures, 263, 273, 283, and this is Kelvin. This is 0 degrees Celsius. So this is 10 degrees below 0. This is at 0. This is positive 10. So that's negative 10, 0, positive 10. So you'll notice that my delta H isn't temperature dependent. That's going to stay the same. My delta S for the system, this is not the surroundings, this is for the system, is going to stay the same. Okay, so these values aren't temperature dependent. So to calculate delta S for the surroundings, I'm going to switch the sign of delta H, I'm going to make that negative, and then I'm going to divide that by the temperature. Now hopefully this makes sense. This is delta S for the surroundings, okay? So what that means is that because of the fact that I'm melting ice, the surroundings are losing this energy, okay? Because if I'm going to melt this ice, that thermal energy has to come from the surroundings, and that's going to flow into this ice. This is why I switched this sign. So all I did here, I took this delta H, I made that negative, I divided it by the temperatures, and I got these values. So I just wrote these in to save you some time. Negative 22.9, negative 22.1, negative 21.3. These numbers are becoming smaller because I'm dividing by a bigger and bigger temperature over here, 263, 273, 283. Okay, now, to get delta S of the universe, okay, I'm going to add the delta S for the system plus the delta S for the surroundings. Now, here's what's important. Notice that when I'm at minus 10 degrees, my delta S from the universe is a negative value, which means that this is not a spontaneous reaction. Oh, and it shouldn't be. Okay? It shouldn't be a spontaneous reaction at minus 10. Ice doesn't melt at minus 10 degrees Celsius because it's below the melting point. Now, when I go to 273, exactly 0 degrees, then delta S from the universe becomes 0. That means the system is in equilibrium. So this is this transition phase from solid to liquid. So anytime you have a transition phase, that means at some temperature, this delta S for the universe is going to reach 0, which means the system is at equilibrium. Okay, you're at a phase transition. Now, when I go to positive 10, and I add my delta S for the system and the delta S for the surroundings, now I'm up to a positive delta S, which means that reaction is now going to be spontaneous. So below, I have a negative delta S from the universe, not spontaneous. At 0, I have a delta S that's 0. I'm at equilibrium. Here, I'm above, the reaction becomes spontaneous. Now, all I did here, I took the temperature and multiplied it by delta S, because I'm going to use this equation over here next, delta H minus T delta S. So all I did here was just get these numbers. So to get this value, so this is going to be my delta G calculation, because delta G is going to equal delta H minus T delta S. So I got 6.03 times 10 to the third, which is just my delta H. This is what I got when I multiplied the temperature by delta S. Now, notice here that my delta H term is bigger than this value. I've got a positive delta G, the reaction isn't spontaneous. At this point, the two values are the same, okay? My delta H and my T delta S, okay? These two values are the same. I have 0, I'm at equilibrium. Once I go above this, then my T delta S term is bigger than my delta H term, and now I have a negative delta G and the reaction becomes spontaneous. So here's what's important, kids, is that you have to look at this in terms of a big picture. Oh, right. My delta S for the surroundings is temperature dependent. My delta H doesn't change, but I can change my temperature. My delta S for the universe, the sum of these two values, if my delta S for the universe is negative, it's a non-spontaneous reaction. If it's positive, it becomes a spontaneous reaction. If it's 0, it's at equilibrium. So what this means here is that, for example, let's say, and these always have to have opposite terms, because you're changing entropy of the system. Like, let's say, for example, in this case, you have like a positive delta S for the system. That means the surroundings have to have a decrease in their entropy. So when you're melting ice, you're increasing the entropy of the ice because it's melting, but you're decreasing the entropy of the surroundings because that's where that energy is coming from. So, again, you have to be able to think through the big idea on this. This takes time, okay? And there are certain things that you just need to begin to memorize. When is it spontaneous? When is it never spontaneous? When is it spontaneous at high temperatures? When is it spontaneous at low temperatures? So keep that in mind. Okay. So one of the things that you can look at to get a general idea about the change in entropy is the moles of gas on the products versus the moles of gas on the reactants. So let's say, for example, that you have, I don't know, I'm just going to make this up, CH4 gas, and you're going to burn that in oxygen, and you're going to get carbon dioxide and water as a liquid, and that's a gas, and we balance this, 2 oxygens, there we go. Okay, so simple combustion reaction. So one of the things you can look at is delta N of change in the number of moles of gas, okay? Which is the number of moles of the products minus the number of moles of the reactants. So in this situation, carbon dioxide is a gas, obviously. So in this situation, I have and as this is going to be important, this is liquid water, not gaseous water. This is liquid water. And you have to pay attention to what that is, gas or liquid. So in this situation, I only have 1 mole of gaseous product. Over here, I have a total of 2 moles of gaseous reactant. So this becomes -1. So here's the deal. If I've got a -1 in terms of this delta N, that's most likely, almost always, not completely, but most likely, going to cause my delta S to also be a negative value, my change in entropy. Because remember, gases have a lot more entropy than solids and liquids do. So by having 2 moles of gaseous reactants, which has a lot of entropy, and then I only end up with 1 mole of gaseous product, that means that odds are, not always, but pretty much, odds are that's going to be the same. Now, if this had been a gas instead of a liquid, so in other words, we're at a higher temperature, high enough temperature that this is actually gas, then I'd have 3 moles of gaseous product and 2 moles of gaseous reactant. And then I'd take 3 minus 2, and then I'd get a positive 1. So if I get a positive change in the number of moles, in other words, if I end up with more moles of product that are gases than I have as reactants, odds are that means my entropy is going to increase, and that's going to be a term of my delta S. Okay? All right. Now, here's the other trend, is that if you have more complex molecules, that means that those typically have more entropy. So if you've got something simple, like let's say, for example, you have carbon dioxide, okay? It's a pretty simple structure. That's probably not going to have very much entropy to it. Now, if you get something weird where you have like a carbon and, I don't know, you got these hydrogens over here, and then like you have an OH group stuck here, or whatever this is. This is going to have, I guarantee you, more entropy than carbon dioxide is. Number one, it's not symmetrical, okay? So basically, the more things, the more microstates that you can have, because this thing isn't symmetrical, the more entropy that you can have. So it's not symmetrical, and it's more complex than the carbon dioxide molecule is. So this is going to have more entropy than just that straight carbon dioxide. Now, on your equation sheet, down here on the thermodynamic stuff, so you've got 3 big equations, and they all have the same format. I'll put it in the same order you guys have. Okay. So here's the story. So this is what's on your equation sheet. These are going to be like the big 4. So let's say, for example, that you want to calculate delta G for a reaction. So there's a couple of ways you can get to that point depending upon what information that you have. One option is that you go to the back of your book and you look up that thermodynamic data. And so one option is that you could go through, like for example, on this reaction with combustion of methane. So you go through and you look up the delta G of carbon dioxide and the 2 times the delta G of liquid water, and you'd add those together, and then you'd subtract these values for methane and oxygen. So that's one way that you can find that value of delta G. The other option is that you could use delta H minus T delta S. So what you could do is that you could find the delta H using this one. So you would go through and you would look up all the delta H heats of formation, enthalpies of formation, of the products, subtract the reactants. Then you do the same thing with your change in entropy for the products and the reactants. So you would have your delta S value that you would put in here. You'd have your delta H value that you would put in here, and you would have to be given the temperature. And then you could find that delta G value that way. Theoretically, no matter how you do it, you should get the same value of delta G. There might be some differences on that, but usually the differences are pretty small because they should get you the same value anyway. So depending upon what you're given in the problem, there's two different ways you can calculate delta G. Now, sometimes, like on your assignment, you are going to be specifically told to find delta S, or by itself, or to find delta H by itself. You would be specifically told these values, and then you'd specifically find this delta G naught. So on your assignment, by the way, I'm just going to give you the answer key to it because this is so important, and I want to make sure that you all have this right. So I'm actually going to send out the assignment and the answer key to it. I'm just going to send you the whole thing because I got to make sure that you all understand how this deal is playing out. Let me see. Got that, got that. Got that. Got that. I'm looking for one problem. Oh, here it is. Okay. So, gotta get done so I can get on the Google Meet. Okay, so here's the deal. We're going to look at this in terms of at what temperature will bromine boil. Okay, so you have liquid bromine, and then we're going to change it into a gas. So we're going to have a phase transition. So you've got to figure that your delta S is going to be a positive value because you're going from a liquid into a gas. My delta H is a positive value because I've got to dump energy into it. So right away I have two positive values, which means that this is going to be temperature dependent. It's not always spontaneous, because if it was always spontaneous, then I wouldn't ask this question because bromine would always boil. So this is driving it away from spontaneity. This is driving it towards spontaneity. The other way that you can look at this in terms of a positive delta H is that you have to break bonds. You have to break the bonds that hold the bromine together as a liquid. So that's another key indicator that you can look at it as an overall trend, is if you have to break a bunch of bonds and not form very many, you got to figure delta H is going to be a positive value. Because remember, you have to put energy in to break bonds. Okay, so I'm going to set delta G equal to 0. I'm going to move this over here. So I'm going to have T delta S equals delta H. And so my temperature then is going to be delta H minus or divided by delta S. Now, what you have to watch here are the units. So this is in kilojoules, this is in joules. So you have to make a choice. I don't care which one you do. You either need to change this into joules and get 31.0 times 10 to the third, okay? Or change this into kilojoules by dividing by 1,000. So I changed everything into joules, and you get 333 Kelvin. Okay, if you do the math, I'm trying to rush through this. Now, if you subtract 273 Kelvin, you get into Celsius, you get 60 degrees Celsius. So what that means is that the boiling point, and this is physically what this means, so that means the boiling point of bromine is 60 degrees Celsius. So if I'm below, because I've got a positive delta H and a positive delta S, so it has to be above that point to be spontaneous. So this is what's important in this one. Room temperature is about 25 degrees Celsius. So what that means is that bromine is going to exist as a liquid at room temperature, okay? Because I'm below that critical point of 60. Now, if this had been, instead of 60 degrees, let's say that had been 10 degrees. What that means is that at room temperature, 20 degrees, bromine would exist as a gas because we would be above that critical point. So, because this is 60, this is why bromine is liquid. You all have made bromine with electrolysis. We dumped the little electrodes in there and we had bromine played out. Okay, you all have seen that. It's a liquid because it's below that point. Okay, I'm going to wrap this up so I can get it on the Google Meet. I will send out the answer key to the assignment and all that good jazz. So, that's it.